Hello. In this talk, I'm going to give you a brief introduction to the wonderful world of Bayesian statistics. I'm going to talk about both the philosophical differences as well as some of the applied differences compared to conventional statistics you may be familiar with. My name is Dan Lane. I'm in the final year of medical school at the University of Calgary, but most importantly, I love statistics. My interest is in translating data to improve clinical practice, and as you'll see, I think Bayesian statistics does this ideally. Here are the conclusions I hope you take away from this talk. First, statistics is just about drawing lines. Second, Bayesian statistics versus frequentist statistics, which is the conventional form you may be familiar with, is just a difference in philosophy. Finally, I think Bayesian statistics has applied benefits when you're translating data to clinical practice. So let's start with the basics. Why do we do statistics in the first place? Well, I would argue that the goal of statistics is to use study data to, first, predict outcomes among future patients. These may be outcomes based off of patient characteristics, such as their likelihood of having a disease or risk factor for developing a disease. Or second, predicting the outcome of a patient given some intervention, such as in a randomized clinical trial informing which treatment is most appropriate. Second aspect of statistics is to explore uncertainty. We know that study data are only representative samples of a population. Therefore, we need to infer what the uncertainty is among that population in order to have a better idea of the generalizability to our clinical population. How is this done? Fundamentally, studies get some data and then draw a line using statistics in order to understand the relationship among those data. You may recognize this formula from your high school algebra class. This is the simple formula for drawing a line. The line helps you understand the relationship between some data and some outcome. I'll give you an example to show you how this works. This is some data I have looking at the relationship between the number of patients presenting to the emergency department during the COVID pandemic. The gray line represents 2 years of historical controls, while the black line represents the number of patients presenting after the first case, represented by this dotted line. The line for this relationship between the number of cases presenting and the COVID pandemic is shown here, where 1,079 represents the baseline rate of patients presenting to the emergency department. This parameter represents the change that occurred following the first COVID case, a decrease of 379 patients. Finally, this term represents the slope of the line following that first case, with 1.6 more patients presenting each day. This formula gives all the information that you may need to address questions. For example, you've got the baseline rate that occurred in previous years. You've got the change or the effect that COVID produced. Finally, you've got the recovery and an estimate of how long it's going to take to get back to that baseline. So that's what I mean when I say statistics is just about drawing lines. So let's talk about some of the philosophical differences. First, let me introduce you to Thomas Bayes. Thomas Bayes was a Presbyterian minister during the Enlightenment. It was said that he used mathematics to argue for the possibility of religious miracles. He wrote a number of manuscripts in his lifetime, but he's most famous for this manuscript, an essay towards solving a problem in the doctrine of chances, what we call probability theory today. This manuscript was actually published posthumously in 1763 by one of his friends who recognized the value of this work. In one of the footnotes of this manuscript, he develops the formula for what he is now famous for, Bayes' theorem. What Bayes' theorem does is it allows you to take prior probability for some event occurring A. So this is your prior knowledge of the likelihood of an event occurring. It then allows you to combine new data about the event A in order to update your understanding about the probability of some event A occurring given the data. Although this may sound a little complicated, What I want you to recognize is that this is simply learning in a mathematical form. Let me illustrate this in words. Thinking about the weather, a Bayesian would say, it's November, I see clouds outside, therefore it's probably going to snow today. That's your prior, your data, and your posterior conclusion about the event. If this is the way that you think, you probably already think like a Bayesian. I'm going to contrast Bayesian statistics with frequentist statistics. Again, this is the form of statistics you're probably most familiar with. One of the fathers of this brand of statistics is Ronald Fisher. He's the statistician that invented the p-value and is responsible for a large majority of statistics we see in medicine today. I'm going to represent frequentist statistics using this formula. This formula suggests that as the number of trials you have, or the amount of data you have, approaches infinity, then the observed frequency for some event will begin approximating the true frequency, or the population frequency. There's two important things to recognize from this interpretation of data. First, it needs to start with a null hypothesis. You cannot divide by zero. Therefore, you need to have some sort of an understanding of where to start. Second, the estimate that you get in the end will depend largely on the number of trials that you have. Let me translate these two implications into the frequentist approach to thinking about the same problem. Frequentists might say, every day is the same, that's your null. Today, are there enough clouds to reject my hypothesis that it will not snow? Again, this is the null hypothesis, the frequency, or the data that's collected, and the interpretation. As you can see from this example, frequentist statistical thinking is much less intuitive. The differences in philosophy arise based off of how frequentists and Bayesians incorporate uncertainty into their estimates. In the frequentist paradigm, they assume that data arise from repeatable events that are presenting randomly. Therefore, their uncertainty comes from when there's a sufficient amount of data in order to be confident that they have a true estimate of the probability of the event. Bayesians, on the other hand, recognize the uncertainty about the probability of the event from the beginning. Therefore, they make a guess, the prior distribution, and then state more certainty in their guess as more data is collected. This means that frequentists assign uncertainty to the data arising, where Bayesians assign uncertainty to the parameter estimate itself. How is uncertainty actually represented mathematically? It's through the concept of probability. Frequentists will assign the probability to the data arising, given that they believe that the parameter estimate is unknown but fixed, whereas Bayesians assign probability to the parameter estimate in order to get an estimate of how much of the outcome is explained given that the data are fixed. In the statistical models, probability is represented using a distribution, which is a mathematical function that represents the uncertainty. The one you'll be most familiar with is the normal distribution, also called the Gaussian probability distribution. Distributions represent the most likely estimate with the peak and the entire range of the estimate with the tails of the distribution. Therefore, under the frequentist paradigm, the process for which data arise is considered uncertain, and therefore this is represented using a distribution. However, parameter estimates are assumed to be fixed. Under the Bayesian paradigm, data are assumed to be fixed, and parameters are considered uncertain. Therefore, the parameter estimates are represented using a distribution. These differences manifest most clearly in the way that frequentists versus Bayesians display their estimates of uncertainty. Frequentist estimates are about the chance of making a wrong claim. Think of the definition of a p-value or a confidence interval, where Bayesians simply provide the strength of evidence for their estimate directly. That is the difference in philosophy between a Bayesian and frequentist paradigm. So let's talk about the application of this. With Bayesian estimation, you always need to start with a prior distribution. Remember, these prior distributions are explaining the parameter. In other words, they're explaining the treatment's effect. Therefore, you're going to mathematically explain what you think are the possible treatment effects before collecting data. One example of a prior distribution would be a uniform distribution. In this example, the uniform distribution gives an equal probability of any of the treatment effects between a value of -5 and 5. Another prior distribution, more commonly used, is a normal distribution. In this case, the highest probability is a treatment effect equal to 0, but there's some uncertainty about whether that treatment effect is negative or positive, spread out amongst a standard deviation around 0 of 5. So what do we do with this prior distribution? Well, starting with that guess or prior estimate of what the treatment effect could be, we then collect some data and combine these data with the prior distribution in order to get an estimate of the effect, which we call the posterior distribution. In words, this would be given some sort of assumptions about the treatment effect, what we call priors. You're going to count all the ways that the data could possibly explain the outcome, and the ways that are more consistent with the data are more probable. And the reason I put up this picture here is to show that sometimes treatment effects are not perfectly normally distributed, such as this one. You can have random humps representing different estimates that may be more probable in occurring. Easy way to conceptualize this is looking at estimating the probability of each of the electoral candidates winning the US election. Because of the way that the Electoral College is set up, a candidate can only get a certain number of votes. And so some count of electoral votes are far less likely than other counts, as well as by including information about what states the candidates are more likely to get, we can estimate the eventual count of Electoral College votes that each candidate will get. So that's why you see these random humps in posterior probability distributions, because it's all the possible estimates given the prior and the data collected. What about representing uncertainty? Well, with the Bayesian paradigm, once you've estimated your posterior distribution, you can just describe an interval that's relevant to the conclusions from that distribution. We call this a posterior interval or a credible interval, and it simply represents the proportion of estimates expected to be within this range. So for a 50% interval, we would expect 50% of patients to have an estimate of effect between this point and that point. So it's very intuitive and provides readers with information they need to know. Let's contrast this with the frequentist confidence interval, which is actually the proportion of experiments when repeated infinitely, where the true estimate would be captured within this range. So it's not actually giving you an estimate of the uncertainty, it's giving you a proportion of experiments where you would expect to have an estimate in that range. Not quite as applicable for clinicians. So what can Bayesian analysis be used for? Essentially anything that you're applying a frequentist analysis to, such as multivariable regression, meta-analyses or network meta-analyses, clinical trial analysis, and observational study analyses. We also see this in multiple fields that have applied need based off of those estimates. For example, the Large Hadron Collider in Switzerland used Bayesian analysis to combine all of the data that they had in order to estimate when they had truly discovered the Higgs boson or God particle. Search and rescue services use Bayesian estimation in order to estimate the most likely place for a survivor in the ocean. Or astronomers using Bayesian estimation and continuous data collection in order to estimate the most likely place where they can detect new planets outside of our solar system. So that represents some of the applied benefits of Bayesian estimation, and I'm going to show you a couple clinical examples now. Here was a study that looked at the use of ECMO, which is heart-lung bypass, in order to rescue patients that had severe acute respiratory distress syndrome. Their question was, is there a difference in 60-day mortality for patients that were treated with ECMO compared to conventional ventilation? Unfortunately, this study had its stopping rule met for futility, and therefore they stopped the trial early at only 249 patients. The results were 44 patients in the ECMO group and 57 patients in the control group died at 60 days, to give them a relative risk estimate of 0.76 and a confidence interval that crossed 1 with a p-value of 0.07. Here was the difference between the two groups in terms of their probability of survival, with the ECMO group having a higher probability of survival throughout the study. But again, because of that p-value of 0.07, the study concluded that they were unable to show ECMO-reduced mortality in patients with acute respiratory distress. What I think they actually should have concluded was that the trial was underpowered to detect differences in mortality after they did a multiplicity adjustment for their interim analyses. So some Bayesians came along and decided to do a post hoc analysis using the Bayesian paradigm. They set numerous prior distributions in order to do these analyses. The dotted line here indicates the minimally clinically important difference as defined by the original study authors. The Bayesians then defined a uniform distribution, which is an equal probability of effect throughout the entire range here. They defined a skeptical prior, which is a prior that's centered at 1, which is no effect, but allows for a decreasing probability for benefit and for harm on either side of an estimate of 1. Finally, they set an enthusiastic prior, which was centered at the minimally clinically important difference, but allowed for a greater benefit or more harm on either side of that minimally clinically important difference. What did they get? Well, here is the estimate for risk of mortality based off the model using their skeptical prior. The skeptical prior is shown here in orange. You then see the data that's added in and their posterior distribution of effect represented by the dark line here. So in their study, asking the question, what is the probability that ECMO reduces the risk for mortality? In other words, what's the area of the probability distribution that's less than 1? They estimated that this probability was 96%. This gives them the relative risk estimate of 0.78, very similar to the Frequentist estimate. However, majority of the probability distribution was less than 1. So what were the differences in inclusion again? Well, the original study concluded that they were unable to show ECMO-reduced mortality. Using the same data, but a Bayesian approach to the analysis, the Bayesians concluded that there was a 96% chance that ECMO reduced mortality. So consider if you had a loved one with acute respiratory distress, which one of these therapies would you want them to have based off of this same data? If you're interested in trying this for a different clinical trial using different estimates, you can use this online calculator that I helped develop by simply scanning this QR code with your phone. Let's talk about an example of an observational study using a Bayesian paradigm. In this study, I asked the question, does time in the emergency department worsen psychiatric illness? So among patients with psychiatric disease, we looked at the time that they were stuck waiting in the emergency department before getting admitted to a psychiatry ward, and how this time was associated with their length of stay in hospital as a representation of the severity of their psychiatric illness. There were some unique challenges for this exposure. The first being that the time waiting in the emergency department differed considerably based off of hospitals in the city. It also depended on the specific psychiatric condition that the patient had, because this would control how strict of observation or the type of unit that they would be able to go to. With a Bayesian model, I was able to estimate each of these effects individually while sharing information across these effects. This is a process known as hierarchical modeling. So on the left, you can see the individual estimates for the boarding time or length of time spent in the emergency department for each of the 4 hospitals in the city and how different they actually are. As well, you can see the differences in the amount of time that patients would wait in the emergency department based off of their actual underlying psychiatric diagnosis. So all of these differences I was able to account for within a single model. This led us to the conclusion that boarding time slightly increased the hospital length of stay. For example, a patient that was boarded for 24 hours had roughly an increase of 0.01 days, which is not very high. But the benefits of doing a hierarchical model is we were able to account for all of the uncertainty that may have contributed to the differences. This is the posterior distribution for how boarding time changes the length of stay for a patient in the hospital. And I was able to estimate that the probability that an increase in boarding time would increase the length of stay was 0.92. So there's a 92% chance that longer in the emergency department would result in longer in the hospital. You can then present those estimates to hospital administrators or end users, and they can interpret it how they want. If they think that this change is relevant, then they may seek to intervene on the exposure. So that's an example of an observational study. Where else can you use Bayes, and where might it help in clinical practice? I alluded to this earlier, the concept of the p-value. There's been considerable amounts of debate about what threshold is appropriate or if a threshold is even important, with this viewpoint being published a few years ago proposing to lower the threshold to 0.05. But the important thing to recognize is that a p-value is a probability about the data arising, not a probability about the hypothesis or about the effect that we care about. With Bayesian analysis, you simply estimate the probability of effect directly. Therefore, you don't need a threshold or to have arguments about what threshold is appropriate. We talked about how the ECMO trial was underpowered, likely because they did a multiplicity adjustment. Multiplicity adjustments are because in a frequentist paradigm, when you're doing many comparisons, it increases the chance that you're going to have a chance association. Therefore, every new test that you do, you should be conducting an adjustment. But this is a problem because the frequentist paradigm is assuming that the data are uncertain rather than the parameter is uncertain. In the Bayesian realm, because you're constantly conditioning on that data and not assuming that the data are arising through random events, you can always estimate new estimates based off of more data coming in. So this is an example of a trial that's using Bayesian or updating. Every time they get more data, they do a new estimate of what the potential treatment effect would be. And as you can see, based off of the prior, which was the dotted flat line there, the treatment effect is refined as more data comes in and gets more precise. So this is exactly what we would expect to occur as more data comes in. This approach has been approved by the FDA and Health Canada for both drugs as well as medical devices. Here's another problem that is quite familiar to us right now. The idea of small effects or emerging diseases where you don't have a lot of information. These oftentimes require larger or more expensive clinical trials, or is a scenario where you need information fast. Using the Bayesian paradigm, you can integrate previous results or prior knowledge into your treatment effects in order to understand these small effects or emerging diseases faster. Finally, there's the problem of clustered or hierarchical data. I alluded to this in the observational study example, where differences in the boarding times occurred at different hospitals. We know that when you have the same patient or the same unit or the same hospital, those patients are going to be more similar to each other than they are going to be to patients in other clusters. The important thing is by ignoring this clustering, you're assuming all observations are created equal. And this may be a false assumption that decreases the accuracy of your estimates. In Bayesian analysis, hierarchical modeling is the default, where you account for clusters within the data seamlessly. Here's a good review article discussing the benefits and the ease of Bayesian hierarchical models, where you can estimate the unique cluster effects while sharing information across the clusters in order to make better predictions. If you would like to see a visualization of why hierarchical models are superior in terms of estimates, you can scan this QR code. This is a philosophy that I'm sure you've heard before, particularly in epidemiology, where all models are wrong but some are useful. The Bayesian models give you more information that are coming out of the data and allow you to make estimates that are more generalizable. So, what do I conclude from this? First, I think that Bayes better aligns with our intuition and the questions that we ask, particularly from a clinical realm. Bayes gives you more information about the data and more relevant information about potential treatment effects by estimating the probability that a hypothesis or an effect is significant rather than the probability that data arise. I think it's an advantage that Bayes forces you to specify your assumptions explicitly within that prior distribution. This allows other researchers or reviewers to examine whether they think that those assumptions are appropriate or not. However, frequentist inference is definitely faster, doesn't require as much computation time on your computer, and is more broadly used, at least for the moment. If you'd like to learn more about Bayesian inference, there's a free YouTube-based course called Statistical Rethinking by a professor in Germany. He has 3 years going on 4 years worth of lectures on there, and they're fantastic. So I hope you found this lecture informative and thought-provoking. If you have any questions, feel free to reach out, and I'd be happy to discuss this further with you. Thank you.